The theorem. Let A and B be invertible matrices of the same size. Then A inverse is invertible, and its inverse, as you might expect, is A. Just like when you do 1 over a number, you get back the original number. It's the same with matrices, except we're using the inverse symbol instead of 1 over. If C is a non-zero scalar, then CA is invertible, and CA inverse is 1 over C times A inverse. That's just like it is for real numbers. If you take a product of two things to the minus first power, you get the first thing to the minus first power times the second thing to the minus first power. A times B is invertible, and the inverse of AB is B inverse A inverse. Note the change in order. To help remember it, I will call this sometimes the socks and shoes rule. The reason being is that, okay, if I first put on my socks and then put on my shoes, well, and to undo that, I need to take off the shoes first and then take off the socks. The transpose of an invertible matrix is invertible. And if I take the transpose of A and take its inverse, and the inverse of the transpose is the transpose of the inverse. Finally, if R is a non-negative integer, then A to the rth power is invertible, and its inverse is the rth power of A inverse. So the only one of these is not exactly the same as it is for real numbers is part C. And to remember how part C works, you just need to remember the socks and shoes rule. I'm not going to go ahead and prove all these. You can look in the book to see the proofs, or you can try and do them yourselves. They're not that difficult. Just as we do with real numbers, we can now make sense, using part E of this theorem, of negative powers of a matrix. So what we do is we define A to the minus rth power to be equal. We define this to be A to the minus first power itself raised to the rth power, which by part E of the theorem is the same as A to the rth power inverted. Then we get that A to the r times A to the minus r is equal to the identity matrix, which you can also think of as A to the 0th power, just like we do with real numbers. By taking the 0th power of a real number, we get 1, which is the 1 by 1 identity matrix. And this allows us more generally to define, or to say that therefore it gives us A to the r times A to the s is A to the r plus s for any two integers, r and s. Before, we just had powers for non-negative integers and for -1. Now we have powers for all integers.